Okay, hello everyone. Welcome to the Data Management Practices track. I'm Aldis Carlos Carlosques, your host from the company EIS, Technology Innovator for Insurance. I'm also the founder of growing community Techies of Baltics. Greetings from our knowledge partner Pact, who will award the most active attendees with free ebooks. So, how to be an active attendee? Rate sessions, leave comments, be an active attendee. And then also, Manning Company will hold a competition for winning ebooks at their virtual booth. So, go check out Manning Company's virtual booth. So the first talk of this track will be presented by Bas Geerdink. Bas, you there?
Yes, hello.
Oh, good. From the company AI Zonek. I hope I'm pronouncing it correctly. And Bas will explain us about the need for MLOps. He will dive into the tools and techniques and give some examples of real world solutions. So, all focus, all attention on Bas. Feel free to show the presentation and take over. Good luck.
Yeah, thank you very much, Aldis. Hello, everybody, and thanks for joining my session here at the conference. Let me start by sharing my slides. We're going to talk about MLOps, and of course, a bit in the context of DevOps, because that's the topic of the conference today. MLOps is the practice of running machine learning models in production in your enterprise, whether you're running it in a small organization, government, or a big enterprise. You have to find some way to, of course, productionize your machine learning models. So a little bit about myself. Yeah, I work indeed as a consultant, mostly as a technology lead. My own background is artificial intelligence, so I'm also a data scientist, but I'm not really specialized in that anymore. But I still know, some of the algorithms and models, etc. And you can find me on LinkedIn and Twitter and somewhere else. So I would be happy to connect. So please do. I also wrote a couple of books and articles and some other sources, including a Pact book called the Artificial Intelligence Infrastructure Workshop, which is a hands-on book about the MLOps topic. Actually, it's a practical book that guides you through some of the technologies that we also discussed today. And recently, it just came out is an MLOps playbook from the consultancy company Equal Experts, which also recommended to read. Right. Let's start with the perspective of machine learning, of a data scientist, because that's usually where people start when they are interested in this kind of topics. They want to predict something in their company. They want to do something with AI or machine learning. What usually happens is you hire a couple of data scientists and they start with model building. They start with this. They spend a few years in university, usually learning all kinds of complicated algorithms, visualizations, all kinds of dedicated tooling that they're using and frameworks that they're using to make predictions. It is of course a subject in itself. It's one of the biggest jobs out there at the moment, and it's something that people spend a full career on learning, and as certainly a full university career on to grasp the depth of all the machine learning algorithms and frameworks that are out there. But what people are usually learning is this. They learn to and a notebook is basically a browser-based tool. Usually it's Jupyter. That's the main notebook tool that allows you to quickly evaluate data and write some statements and see the results of those statements, which is great. It's a fantastic tool when you're doing data analysis, because you can easily display graphs, data tables, those kind of things. So it's a great way to work with data. However, it's not really intended to run in production, because this is a data visualization tool. It's not a full production tool. It's not something that you can easily incorporate in your enterprise. Although some companies try to do it, it's actually not really the recommended way to productionize your model. So although this is a great tool to basically experiment with data and maybe even build a first iteration of your machine learning model and discuss the results with stakeholders and so forth, you should realize that this is only a very small part of the entire landscape in your organization. And this is what this diagram depicts, is from a famous article from a few people at Google already from 2015, where they say, okay, there's actually this model that we built, this algorithm, this very complex code that you spent years on learning, is only still a very small part. This is black box here in the center of your entire application landscape. And I think everybody of us will recognize this, if you're in data science or not, because this basically goes for every part of source code that you have, whether it's a machine learning model or maybe something else. Maybe it's a web page, or maybe it's an API, some code that you programmed in to be served as a microservice or so. The tooling and technology and monitoring, etc., around that to prepare the data, to make it stable, to actually very important. So that's why we have MLOps. MLOps is a practice, a set of best practices, more a culture to bridge this gap, from machine learning specialists, data scientists that are very specialized in developing algorithms, the gap from those people to the rest of the organization who are more specialized in general software development and operations. And I want to go a step back first to DevOps, because we had this kind of gap, before. This gap was between developers and operations. And of course, I probably don't have to tell this in the DevOps Pro conference, but it would be good to realize that 10 years ago, or maybe even longer ago, there was this gap between developers and operations, where we did waterfall development and things were being built in a different team than that they were managed in. So people were developing software in a specialized team or department. When the software product was ready, it was basically thrown over the wall, and some other team, they were specialized in operations and maintenance. They were maintaining it from that point. But of course, we said, hey, that's not really efficient. So when the DevOps revolution came about 10 years ago, we started to combine those people in one team. We said it's much more efficient to combine developers and operations in one team, to have a shared responsibility for an end product, which is a part of software that runs somewhere in our enterprise. And once you do that, you can also introduce very efficient practices like continuous integration, continuous delivery, and continuous monitoring to keep on iterating. That's of course the link to agile development, to keep on iterating to improve your product continuously. It also means that some of the developers need to do some operations, and some of the operation guy need to do some development. Well, that's part of the job. Well, MLOps is kind of the same, but now we introduce another specialty. Instead of DevOps, we introduce machine learning. So the machine learning specialists, the data scientists, are no longer somewhere in a separate team or department in a dark corner of the building, or they have their own floor or whatever. No, we integrate them into the teams which are already operational, and they have a shared responsibility, and they have a joint effort to build and evolve a certain software application. Only now it includes a machine learning model, which is what makes it more interesting. And the goals of MLOps are therefore almost the same as DevOps, to gain trust and speed when you're developing these kind of applications. And also the same practices that we apply in DevOps, for example, continuous integration, continuous delivery, should be applied to these machine learning models. Continuous monitoring, logging and alerting, etc. But then on a little bit of different flavor, perhaps, than you're managing and checking regular applications. And also comes with some new roles and responsibilities, because of course this machine learning model, that's a highly specialized artifact that you certainly introduce into a team. So what you see nowadays is that there's roles such as data scientist and machine learning engineer those are being introduced to actually build the models, train the models, but also integrate them into the software. And there's special tooling for that, there's best practices for that, etc., that I will actually dive into a bit later. But it's good to realize that of course this adds some complexity to your team, because if you just have a backend to manage, then it's probably a bit simpler than a backend including machine learning model, because that machine learning model comes with its own type of characteristics. It has to be maintained, evolved, and monitored in a certain way. This, of course, does not mean that you have to add more people to the team, because it will be perfectly possible to say that one person can have two roles. For example, you could have a dev engineer who is also a machine learning engineer, or you could have a data scientist who is also a data engineer. But it would be good to realize that these kind of roles are important in the teams that you have when you're doing MLOps. Well, some best practices to conclude this section with to run these models in production. What I would recommend is to treat those machine learning models as basically an ordinary artifact on the basis in your software application. Just like some other artifacts you probably have around, like a piece of video or an image that you use in a website, for example, or maybe another file-based asset somewhere in your backend of your system. All of those assets have to be properly managed, so they have to be versionized, they have to be governed. So data governance and machine learning file governance is also very important. So track the history. They have to be owned by somebody, etc., etc. That's really the basics of handling these kind of artifacts. In the end, your machine learning model is just a file that you use somewhere. So that's fine. But on the other side, it's also a living artifact. So it's not so static as you would have like maybe a normal piece of your infrastructure, which does not evolve, because that's the characteristic of machine learning. Machine learning models grow and evolve and become better in time based on historical data that they keep on training on. So your machine learning model is never ready. Is never finished. Let's say you train a machine learning model on customer behavior. The behavior of your customers 1 year ago will be different than the behavior of your customers today. And of course, think about everything that changes. The environment changes. The people change. Your products change, etc., etc. So your machine learning model will also have to be retrained periodically, and that means that it also needs to be monitored and tested continuously on maybe some different aspects of the model. You should, of course, monitor your model and your infrastructure on the standard characteristics and the standard metrics that are there for software, and we call it the technical metrics. For example, is the performance good? Is the latency is it good enough for our requirements? Is the CPU load not too high? Those kind of things. But next to that, it's also very important to monitor your machine learning model on what we call the business metrics. and that's actually the performance of the model itself, because this model continuously gives out predictions. But what if those predictions suddenly, become, strange? Because there's, for example, predictions that are out of the ordinary compared to the average number of to the average prediction that, for example, that were handed out maybe a week ago. So let's say you predict, one real life example I'm working on currently, we predict delivery times for customers. So when a customer orders a product, we predict how long it will be, how long it takes to get the product delivered to his house. Well, let's say the average prediction that this model normally gives is 2 weeks. And now suddenly this model, since the latest version of the model that we retrained and put in production last week or so, suddenly these predictions go up to 4 weeks or go down to 1 week. Then of course something is wrong. It's not correct. Maybe the training data was not correct. Maybe you made a mistake in the algorithm itself, etc., etc. But those are the things that you should be monitoring. It can also have a reasonable explanation because, for example, maybe one of the suppliers that is producing these products is going bankrupt or so, and suddenly the delivery times are extremely high because there's a shortage of products or material or so. Okay, that also can give a reasonable explanation. And in that case, the model actually did a good job of predicting that, because then apparently this supplier capability was one of the features that the model was trained on. But you have to be aware of those kind of metrics. So not only the technical metrics, but also the business metrics. And then some terms come into play, like data drift. What you don't want is your model to be diverting too much from the data that was trained on. So you want your actual model, the actual data that your model is working on, to be as close to the data that it was trained on. And also you have data drift, and your model will give different predictions because it was just trained on different data. Right. We're going to talk a bit about the architecture, about how we're going to do how we want to do that. And let's start with an overview picture that I created, because if you search for MLOps or machine learning models in production or model serving or something else, what you usually get is very complicated diagrams or architectures or lists of tools, and you don't know where to start, and it's very, very complicated. It's very big. But so I tried to make the most simple picture possible to distill the essence of what it means to run a machine learning model in production. And I came up with this diagram. And so far, all the systems that I've seen and built, and all the other architectures that I worked on fall into this kind of reference architecture. So this gives me a good idea that this is somehow correct, that it is still holding up. So what you can see is that there's basically, in any machine learning system, there's two parts of the architecture. There's a real-time part and there's a batch part. Starting with the batch part here on the lower side, there should be a batch process in your architecture that has the goal of retraining your model. As I already said, this model that you have, this machine learning model, will keep evolving. You cannot say, okay, I trained the model once a year ago and now it's done. No, that's the characteristic of the machine learning models is they get better over time, or more accurate. They need to stay accurate based on new historical data that come. What you need to do is you need to gather data as features for you while your model is running in production, and we store them in a feature store, and that's basically a dedicated database to store these kind of data points. So after a certain while, let's say a week or a month, or maybe on short run, maybe a day, or even maybe an hour or so, you have to run a batch process to retrain your model and to publish your new artifact model in a dedicated store called the model registry. Again, it can be a simple tool. It can be a database or a file share, or maybe it can be a very complex tool that you bought somewhere. But this is the essence of the batch process: gathering historical data, running a periodic batch process to train your model, with the result of a model file, an artifact that you store in a model registry. Once you have that in place, this model, of course, needs to be used. So it needs to be served somewhere, so it can be scored. Scoring a model means getting a prediction out of the model, or executing the model. That's also some term that's being used, and that is usually done in a real-time fashion, because this model runs somewhere, maybe on your website or on your application, whatever it is, in your app or in an embedded system. It can also be actually running, in a sort of a batch fashion, because I've seen systems where actually the model evaluation is also done periodically. Well, that's of course also possible, but usually there's some kind of real-time process that says, okay, I need to get continuous predictions out of my model. And that's the top part of this diagram, where you usually have some data preparation, because the raw data that you get from your systems, let's say a website or a finance system or so, is usually not in the right format yet to give to your model. You have to do some data preparation, some feature preparation. Once that is done, so if the features in the right format, you give those features to the model, and they give the model gives a prediction. They give a score. The score it also usually is not in the correct format yet. It's usually a number, for example, from 0 to 1, or it's maybe a category, but then also as a numeric value if you do classification of data. But so that data needs to be interpreted. So there's also some post-processing that needs to be done. For example, the model gives a score of 0.85. Okay, what does it mean? Okay, that means in our system that we will show an advertisement to the customer. Or let's say you have a classification system. The model gives the result of 5. Well, that number 5, what is that? Okay, my post-processing system knows that, okay, number 5 means that, let's say, a credit card transaction is approved and can, the money can be paid if you're doing, for example, fraud detection or so. So this is the high-level kind of reference architecture for all of these systems. Now, there are some nuances here, because, for example, some of these will be doing online learning, what we say. What they say basically is that we don't care about, we don't want to train our model every week. We want to train it continuously. And that's a very modern way of building machine learning systems, also a complex way, but still that it's probably still a batch process, because this batch diagram at the bottom, this batch process, is then just very quick. It for example runs every minute or so. And you can say, okay, we're continuously updating our model, so we're retraining all the time. Sure, okay, but it's still kind of a batch process, more like a micro batch process that happens in that way. And what I said already, also the real-time pipeline on top could also be batch. So you gather some data, then you wait a while, and then you do all the score evaluation of that batch that you collected. So you get it. But the way that these things are working together is still the same. Right. So if you look at some examples of architectures for MLOps, you'll once you have this picture in your mind, you will recognize the same patterns everywhere. For example, the Google Cloud architecture for MLOps has this same kind of pipeline. Only, of course, they have filled it with Google products, because they want to sell their tools, their products. But still, the reference architecture holds. There's a training pipeline here that does the same kind of things. It collects the data, it retrains the model. A model artifact is produced to a model registry, which is here is literally called a model registry in this case. And that model is then served in a real-time API in this case, model serving over here. Same goes for Amazon, exactly the same kind of patterns, but again with the Amazon tools, and Azure has the same kind of architectures. This is actually an example from Microsoft, where this is a dedicated architecture, which I also find very interesting for the Internet of Things, for deploying models to your edge devices. So those are of course not the cloud-based tools, but the microprocessors, the microcomputers, Raspberry Pi kind of devices, where the model is actually being evaluated. And the interesting thing about that is that this diagram here that I showed you, of course, does not say anything about the location where you serve and score the models. This box, this model scoring, I put API between brackets because usually that's an API that runs on the cloud. It doesn't have to be an API on your cloud infrastructure. It can also be an edge device. It can also be a computer. Yeah, it just has to be deployed somewhere where it can be used in real time. And an example of an edge device or an architecture for edge devices is this Azure IoT architecture, where you actually deploy your models to your edge devices. And one example that I'm working on currently is from a company called Wayfair, which is a retail organization where basically we have an architecture to predict things for customers, including just the delivery times that I showed you. We have a combination of Google-based, cloud-based tools and some on-premise data stores and some monitoring tools that you see here. But again, following the same pattern, and I try to highlight them, the patterns with this dotted boxes, the real-time and the batch pipelines that are joined together by the web shop, the backend, which sends, of course, the historical data via a Kafka bus to the feature store that we have. All right. Only now I want to talk about tooling because so I think this is the proper way to do. You should, when you talk about MLOps, first think about the culture, think about your team, think about how you want to structure this, think about the architecture, how you're going to set this up, and only then think about, okay, now we should find some tooling to do this. And I don't think this is actually the most important thing, but of course, people are still very interested in what kind of pieces of the puzzle, what kind of tooling you need to have to do this. But please realize that this is not the most important thing. You will find a tool that suits your organization, but there's a lot. So there is this is only a sheet that I found somewhere that gives some of the tooling options that are possible for doing machine learning in production. And for every tool that you can think of, there's multiple options. There is open source vendors, etc. That could potentially fill your requirements. So third thing, I think the most important thing to realize that if you want to select your tooling, that you ask yourself the questions, what do you actually want? Depending on, again, the culture of your organization. Do you want to, and there's two main discussions here, buy versus build and AutoML versus custom. Because the buy versus build discussion already when it comes to other tooling, basically you have to ask the question, do you want to get vendor products where you buy, where you pay a license for, maybe a software as a service, or something you install yourself, which has a lot of benefits because you can actually use them and don't have to worry about the product maintenance and so forth. Or do you want to build your own tools? And in that case, you also have to maintain it. So it will take more time and effort, but you have more control over your tools. Then the other discussion is AutoML or custom models. And this is an interesting one in the machine learning world currently. because AutoML is taking a bit of a flight. It's becoming much more popular. There are actually a lot of companies who say you can just buy or use our own pre-trained models already. And we also have some tooling around it. So you can just call an API to get a prediction for your data. And in many cases, that's actually good enough. That's all because, for example, in the case of text analysis or image recognition, there are companies like Google that have trained these kind of algorithms on so much data already, so they're already very good. Why would you build and train your own image recognition model if you can already use the pre-trained ones from a company like Google, who has spent years and years on optimizing those models? Or another example is text sentiment analysis. Why would you do that yourself in-house if there's so much great models already that you can just use? On the other side, you can also say, okay, we need what if you need to train a model for company-specific data? Probably there's not a model out there that fits your requirements. You probably have to train it yourself. But then there's a gray area in between. So what if you want to do text analysis, for example, on chat messages that customers are sending to your company? That text messages, chat messages, probably contain some sentiment, but they also contain some data which is very specific for your company. So maybe an AutoML model is not good enough, or maybe it's only good enough for like 80% of the case or so, and maybe a custom model is what you should be using. Well, those are, of course, are interesting cases, and then you should realize, okay, what fits my data, but also what fits my people and my culture. What can we work with? And once you find this out, if you want to buy or build a tool, you do AutoML, custom ML, then you can start selecting the proper technology for your MLOps architecture. Now, for model serving, I want to say that there's also some options there. Some of the tools that are out there, or that you might build yourself, do it in different ways, starting from deploying your model integrated with your application, which the first option. I would not actually recommend it, because this will be a monolithic approach. And nowadays model software development, of course, is all about decoupling things, making things modular, service-based, etc. So a more common and probably better approach is to have a shared service that hosts multiple models, or a microservice approach where you build an API, a service for each of your models. So basically a thin layer on top of your machine learning model that just has the responsibility of integrating your model into the rest of your software landscape. And a special case is streaming data, because there's also dedicated tools and technology and intermediate formats like PML. So PML, Pickle, Joblib are all intermediate model formats that you can use. And some of them, like PML and Onyx, are very good in integrating into Java-based streaming systems, which is usually how you build streaming systems on applications like Spark Switches streaming or Flink, where you need to have extremely low latency, let's say a latency of less than 10 milliseconds or so, where there's not enough time to go across a network to an API somewhere that hosts your model somewhere. There's just not enough time, because the streaming has to be so fast. You need to have your models in memory as close to your data source as possible. And that you can do that by actually combining your model with your business logic in your stream processor. And maybe it goes a bit too far, but what you of course do is you distribute your model then in memory across all of your nodes in your big data cluster that are running simultaneously, so that it can actually evaluate those models in real time very quickly. And another topic that might be interesting is hosting your models on the edge, which is very it's becoming more common at the moment. So because the devices that we can use in IoT, in the Internet of Things, are becoming much smarter, bigger, faster, more powerful. That means that there's no longer a need to send data from your edge device to the cloud and back to get, for example, prediction. You can perfectly host your models on the device itself. You have to be a bit careful, because hosting like a full deep learning network or a very complex model is, of course, not really recommended if you have only a small device. But a relatively simple model, which has just been trained on historical data, doesn't have to be so complex. It can also be a logistic regression model, which is just a mathematical formula. That can be perfectly hosted on the edge device itself, again with the benefits of reducing the latency and also reducing the data that you need to process on the cloud. Some final technologies. Maybe the first one is containers. I would recommend to containerize everything, also in MLOps. Maybe a bit of a no-brainer, but by doing this, you can actually be very flexible in your testing, in your deployments, in your scalability, etc. So also all these machine learning models that you will build and host somewhere, please containerize them. The feature store is not a dedicated technology that we already mentioned. There are also dedicated tools for this. And the nice thing about a feature store as a dedicated tool is that it's not just a database to store feature data, but the good feature stores out there, and I list a few examples here: Feast, Hopsworks, H2O, they all have their own feature store. The good feature stores out there are able to provide you data, features, both in online and offline sense. And online is the features that you need for real-time processing. So that's the top part of our reference architecture, where you need features, for example, the number of sales that a customer made, or any kind of aggregated data that you have collected in the past. You sometimes need them for real-time model evaluation, and a good feature store can produce that immediately with a very low latency, but it can also produce that data in an offline sense when you're retraining your model. Because then you probably also need those kind of values to retrain your model again. But then not only need one of those values, but need maybe millions of those values, because you need to have them for every customer, for example, or for every product that you have in your database. And those features have also been collected in a historic way, and they also need to be produced with a relatively high accuracy. So that's why a feature store is there, and is also actually a recommended tool to consider. And then finally, for workflow orchestration, so if you have some batch process, and we always saw that most of the machine learning systems and architectures have some kind of batch flow, batch job in their architecture for model training or for feature calculation, but some of them also for model scoring. Of course, you need to have some kind of orchestration to schedule those jobs, to orchestrate them, to actually be able to monitor them. So it's also recommended to introduce a good proper tool for that. Well, Kubeflow is one of them, which is dedicated special for machine learning operation, but you can also orchestrate other kind of batch jobs with that. And Apache Airflow is a slightly older tool, which is also very much in use, and a good open source product that you could consider when you're building these kind of applications. Right. So my final slides actually. See, I have a few minutes left, but what we discussed is why we need MLOps. We cannot do full machine learning in production just with notebooks. That's only the beginning of how you start with machine learning. Only the first step. After that, you need to productionize it, etc. And I presented this reference architecture for that. and talked about the integration with DevOps, how this is basically evolving again from DevOps principles and practices. And finally, we discussed some of the tools that you can use to do this in a good way, including the feature store. If you want to know more about these kind of practices, or you want to maybe get some experience yourself or know more about it, here are some resources for that. First one is the book that I co-authored from PACT, the Artificial Intelligence Infrastructure Workshop, which is a really hands-on book. So if you like this kind of thing to work yourself with exercise, etc., then I would recommend that one. There's also the Equal Experts MLOps playbook, which you also already mentioned. And then finally, there's some websites, including a Coursera online course about MLOps and also the vendor-neutral MLOps.org website, where you can get some information from. Okay, come to the end of the session. So thank you very much. And maybe we can answer some questions if there are any.
Hey, thank you. This was very interesting. For now, I don't see any questions from the audience. There are like 70 people super excited. So please post your questions. But in the meantime, so this all is very exciting, but can you share some real life example where you've seen this being implemented and how complicated that was, what benefits you saw, some real war story?
Yeah, so I already gave this example of Wayfair. We're currently working with of the architecture that we have in place. So what you usually see is that the complexity and the challenges are not with building or training your first model, but with the operation side of checking if how that model now is running in production, because that's of course a bit the scary side, right? So if you have a machine learning model, it gives predictions, and if it's integrated in, for example, your website, it's a non-deterministic process that runs. So you don't have full influence on your machine learning model that you have. So that's where the challenge usually is. Once this model is running in production, there need to be constant monitoring about how is this model actually performing. What is it actually predicting? Maybe it can go astray, or maybe it can give any predictions that we cannot explain properly. And if that is the case, and I've seen that happening, then of course it's all hands on deck and check. Is the real time live data, is it different from the training data? Is there something else? That explains why our model is solely predicting not as intended.
Mm-hmm. I'm just trying to picture a situation that I have a train model, I do a version update, it starts throwing new type of logs, some new stuff and graphs, and then could it be that I start chasing the ghost when everything is fine? Actually, the model tells me, hey, you got a problem, there's some new stuff.
Yeah.
And then we need to train it again and again and again.
That's probably what you should realize is, of course, machine learning models have been trained on historical data, and they are very good at predicting patterns. They are very good if regular things are happening. But machine learners cannot do so well is handling unexpected situation, unexpected data. If there's suddenly a big big disaster, or maybe and data and your input data changes because of that, your model starts behaving differently because it has not been trained on that kind of data.
Yep. Okay, I see that we are at the end of our time limit. Thank you very much, Bas. This was amazing.
Thank you.
And see everyone after the morning break.
Okay, see you. Thank you.